So I wanted to talk about a couple of things that we need to take care of this coming week. One of the things that we need to be looking at is we need to be looking at our project and sort of trying to figure out how we're going to do this. Obviously, some of the information gathering is going to change a little bit, but I think we can still do almost all of this project. The one thing that we might not be able to do, we can look at doing presentations online. Maybe we can set up a Zoom meeting or something, and you guys can present to me. But it's sort of difficult because of social distancing stuff with group presentations. So we'll figure out exactly what we're going to do with the presentations when we get closer to them. However, um, I would like to point out that we should be getting back into the action with the other stuff. Technically, task 3 was originally supposed to be due today. Obviously, it was not due today. None of you um, have gotten there yet, and that's okay. I would like to try and have this done um, by the time we're done with the test. So I'm tentatively, and I'll make a post about this in Discord and in D2L, but I'm going to move the due date back to the 13th of April, which will be the same day that the exam will be due. Um, and essentially, the task is not going to change very much, but the way that you're going to be able to execute the task is going to be a little differently. Um, my recommendation is to put together a Google form. Um, has anyone used Google Forms for anything before?
Not before.
Okay. They're actually super
Not
easy to set up. Go ahead.
not
Okay.
not in a while.
So they're really easy to set up. You can set up a personal Google form, and you can make your own. Um, and basically, you can fill it in with questions, and then it'll give you responses. You can also have it set up to. I think by default, it's going to spit out to a spreadsheet too, which will be useful for you to be able to gather your data. Um, Things that absolutely need to be in your survey. You have to have you have to ask them whether or not they would be willing to purchase your product, and you have to ask them how much they would be willing to pay for your product. Some of your research for the product should have given you kind of a ballpark idea, so you can give them multiple choice options. That would be my suggestion. You can also get Google Forms to set it up so that they can just plug in a number for you. Um, but uh, you never know with data. Um, Giving people a lot of options is sometimes a bad idea. The other thing that we can do to fill out this, instead of sort of just emailing it around to people you know, there's actually a Reddit. It's called r/sample size. Um, and basically it's just a Reddit where people post surveys and people take surveys. So if you post your survey over here, you should be able to get some amount of results. I think I had one group last semester do this. They got like 10 results through sample size, which is enough. I'm definitely being a little bit more understanding this semester if you can't quite get as many results as you need, assuming you've showed me that you've made a good faith effort to do so. Okay. So my recommendation is, as a group, make a Google form for your survey. Make sure I have access to the link for the survey, and so that I can see it. And go ahead and disseminate that through some online form. Sample size is a great place to do it. Um, you will need to also turn in some documentation on your methodology. In other words, I want you to explain why you came up with the questions you came up with, and how you distributed your survey. So this is sort of just basic, like if I'm providing data, I'm going to tell you how I got the data and why I got the data I was looking for, right? And additionally, you'll need to document your results. Google Forms will give you back the data in either a spreadsheet, or I think there are some other ways. You can get some charts through Google Forms. I don't want you to use those charts. They're not going to do the things that we want them to do. Um, Go ahead and include a copy of your raw data in some readable format. This should be a list of results. So like a spreadsheet would be perfect. If you have an Excel spreadsheet that you can send me, that would be ideal. And then submit the report as a brief typed document to the Dropbox and D2L. This document should be about 1 page and maybe a little longer due to the survey data. I think it's technically not the Dropbox anymore. I should change that language, but I'll have a spot for it to be turned in. Speaking of things that need to be turned in, I have one product statement from one group. So thank you, the group who turned in your product statement. I appreciate it. For the other two groups, you need to turn that in as soon as possible, preferably before the end of the week. Like if I don't have it by Friday, we're going to start talking about losing points there. So let's get that in as soon as you possibly can. Any questions about project stuff? Okay. I have 8 people in this voice channel and only 6, 7 watching the stream. So whoever is not watching the stream, you should probably double click on my name or click the little live button next to my name so you can make sure you get in and actually see the things that I'm talking about rather than me just talking at you.
Does watching this stream mean
You should be able to see me, Connor. Can you see me?
yes, I can
Then
see
you're
you.
watching the stream. All right. So, math wise, the test is primarily just going to cover optimization stuff. So, I don't want to cover a whole ton of new content between now and Wednesday. I think that mostly I want to make sure that we feel comfortable with the content that we can do. So, I gave you guys a sheet last class with sort of as a review. There were some derivatives and there were about 7 optimization problems. I definitely want to do 7 since it's the new one that we did last class. But are there any of the other ones that you guys want to take a look at specifically?
1 sec. I'm looking it up in my notebook right now.
Okay.
I was able to complete 2 and 3, but I would also like to look over 4 and 5.
Okay. Four is kind of like a simpler version of the quiz you guys did before break. It doesn't give you the same result because I don't have the requirement that the tops and bottoms are require more cost. So it's pretty straightforward. Let's go ahead and start with number 4, and then we'll go from there. So number 4, we want to construct a cylindrical can that will have a volume of 350 cubic centimeters. So volume equals 350 cubic centimeters. And this is a constraint. We also want to minimize the amount of material that is needed to construct the can. So really we want to minimize the surface area of a can, which is S equals 2 pi r squared plus 2 pi r h. The 2 pi r squared is the top and the bottom, and the 2 pi r h is the label of the cylindrical can. Okay. And then so at this point we need to rewrite the objective equation in terms of our constraint. So the constraint is that the volume is 350 centimeters cubed. In other words, 350 is equal to the volume, pi r squared h. So we want to either eliminate h or eliminate r. I think it'll be easier for us to eliminate h. So I'm going to divide both sides of this equation by pi r squared, giving us h is equal to 350 over pi r squared. So our surface area equation actually ends up being, sorry, my screen keeps jumping around, S equals 2 pi r squared plus 2 pi r times 350 over pi r squared. Are there any questions how I got to this point here?
When you plugged in that, when you were at the equation of 350 equals pi r squared times h,
Yep.
where'd you get the pi r squared times h?
So the volume of a cylinder is pi r squared h. It's in the question over here. Make sense?
Yep.
Cool. So at this point, we probably need to we should simplify this a little bit just to save us some time. The pi's will cancel over here, and one of the r's will cancel. So we can write this a little bit more simply as s is equal to 2 pi r squared plus 2 times 350 is 700. So it's just 700 over r. Or even if we want to do s is equal to 2 pi r squared plus 700 r to the negative 1. And then next...
Started recording?
Yes, I did.
Okay, just checking.
Thank you. Next, we will take the derivative. Right, we need to know that we need to take the derivative so we can find our critical points so that we can figure out where this is minimal. So the derivative of this function s prime is 4 pi r plus negative 1 times 700 times r to the negative 2, or 4 pi r minus 700 over r squared. Okay. Once we have our derivative, we need to find our critical points. That is, we need to set the derivative equal to 0. So 0 is equal to 4 pi r minus 700 over r squared, and we're solving for r. We'll add 700 over r squared to both sides. And then we want to get rid of our fraction, so we'll multiply both sides by r squared, giving us 700 is equal to 4 pi r cubed. And divide both sides by 4 pi. So r ends up being the cube root of 700 over 4 pi, which is 3.82 about. Any questions on how we found the critical point here? The algebra for solving for r. Okay, then from there, the last thing we have to do is, the second to last thing we have to do is we need to verify that this is a minimum. And to do that, we need to use either the first derivative test or second derivative test? I would probably use the second derivative test here. We know that s prime is equal to 4 pi r minus 700 r to the negative 2. So s double prime is 4 pi minus plus 1400 r to the negative 3, or s double prime is 4 pi plus 1400 over r cubed. But since r is positive, so our r value is positive, that makes 1400 over r cubed positive, which when added to the positive 4 pi is definitely positive. S double prime of 3.82 is certainly greater than 0. So S is concave down at 3.82. So R equals 3.82 represents a minimum. Or sorry, concave up. You can also do the first derivative test by plugging in a point on either side in the first derivative and show that it changes signs from decreasing to increasing, or changes signs from negative to positive. That also is valid. And finally, last things here, let's go back to the question. So the question wants the dimensions of the can. So we also need to know the height. So we know that the radius will be 3.82 centimeters. And we know that 350 is equal to pi times r squared times h. So that's 350 over pi r squared is equal to h. So we can plug that into our calculator. 350 divided by pi r, but r is of course 3.82 squared. So h is 7.63 centimeters. So the can should have a radius of 3.82 centimeters and a height of 7.63 centimeters. And that's your answer. So notably, this is pretty different from an actual soda can. If you sort of look at this, the diameter of the can is 7.64 centimeters. So essentially, this is sort of like almost like if you looked at it from the side, this can would look almost square. It's a can that has the same diameter as the height. Which is certainly not what a soda can actually looks like. So this is probably not actually, this is not really the best way to make a soda can. It turns out that your top and your bottom are going to be significantly more expensive than the sides when you're actually making a soda can. So the ideal shape is a little different. Okay. Any questions about problem number 4 here? All right. Josh, did you get a chance to look at your notes and figure out the one that you were looking at?
Second, like dimensions for one, the second word problem. Number 3, I mean.
Number 3? Okay, let's go ahead and look at that one really quickly. So let's actually pick this up. Let's move this somewhere else. So we're looking at problem number 2 here. We're going to fence in, or sorry, problem number 3 here. We're going to fence in a rectangular field that encloses 75 square feet. So the area of our rectangular field has to be 75. Okay. We want to determine the dimensions of a field that will require the least amount of fencing materials to be used. Recall that the formula for the perimeter of a rectangle is 2x plus 2y. And the formula for the area of a rectangle is xy. Okay, so of these two quantities, which one are we optimizing? Which one is the thing that we're actually trying to find a min or a max of?
The perimeter equation?
Yeah, so the perimeter is our objective. And the area is actually, this is our constraint. Our constraint is that 75 is equal to xy. Because the area is 75 and the area is also equal to xy. So we can use our constraint to rewrite our objective and eliminate one of our variables. It doesn't actually matter which one we eliminate. In this case, I will eliminate the y variable. So y is equal to 75 over x. So that means that p is equal to 2x plus 150 over y. And that's just substituting in our 75 over, that should be an x, for the y in our perimeter equation. All right. So that means that p is equal to 2x plus 150 x to the negative 1. We should take our derivative. P prime is 2 plus 150 minus 150 x to the negative 2. And then we're setting this equal to 0 and solving. So 0 is equal to 2 minus 150 x to the negative 2, which means that 150, this is really 150 over x squared is equal to 2. X to the negative 2 is equal to 1 over x squared. We can multiply both sides by x squared. And then divide both sides by 2. Which means that x is equal to the square root of 75, which is about 8.66. From here, we need to verify that this is in fact a minimum. So we're going to, again, the second derivative test for these optimization problems is almost always really, really quick. So I'm going to take p prime, which is 2 minus 150 x to the negative 2, and find the second derivative, p double prime, is 2 plus 300 x to the negative 3. Which, if we want to, we can then just plug that in. P double prime of the square root of 75 is 2 plus
The
3.
2 should be gone, I think.
That 2 should be gone, thank you. It's not actually going to affect our answer, but that is very true. So it'll just be 300 times the square root of 75 to the power of negative 3, and we can just plug that into our calculator if we want to. Well, I should clear stuff before. 300 times the square root of 75 to power of negative 3, which is 0.462, which is certainly positive. So x equals square root of 75 is a minimum. And then from here, all that's left is to just state our answer. So let's go back to our question. We're going to fence in a rectangular field and we're going to fence in a rectangular field that encloses 75 square feet. We want to know the dimensions of the field that will require the least amount of fencing materials to be used. So x is equal to the square root of 75, and xy is equal to 75. So y is equal to 75 over x, which means that y is equal to 75 divided by the square root of 75, which is in fact just the square root of 75. So y also equal to square root of 75. In other words, the dimensions that will minimize the amount of fencing used my screen is trying to want to run away from me is 8.66 by 8.66. And that's problem number 3.
So the thing that kind of messed me up with problem number 3 is I couldn't figure out the constraint.
Yeah.
And I mixed up those two equations. So how do you determine like correctly what the constraint and what the objective equation is?
The objective is always the thing that you're trying to minimize or maximize. So in this problem, what were you trying to minimize or maximize? Well, we were trying to have the least amount of fencing material, right? So we needed to minimize the perimeter. So that's basically how you always choose what your objective is. You're always looking at what is the thing I actually am optimizing? What is the thing I am either maximizing or minimizing? So for problem number 2, it was the other way around. I gave you a perimeter and I was asking you to maximize the area. For this question, I gave you the area and I wanted you to minimize the perimeter. For what it's worth, the answer to both of these problems was a perfect square. It turns out that it's not a very interesting question when you just have a rectangle and you're trying to optimize a rectangle. The shape that has the best ratio between surface area, or like between perimeter and area will always be the most symmetrical shape possible. So a circle, for example, is like if you want the biggest possible field for the least amount of fence, you should build a circle. It's actually the best way to do it. But, you know, here we are using calculus for it anyways. Does that answer the question, Josh?
Yes, thank you.
Cool. All right. So I know that we wanted to look at 5. I definitely want to look at number 7 because 7 is the new one. So I would like to jump down to number 7 and then jump back over to number 5 if that's okay with everyone.
Sounds good.
Sounds good.
Sounds good.
Let's move that over here. Actually, we're going to move here so I can stop. I think what's happening is I'm hitting the scroll bar. Try to open that a little more. Okay, so we're working for a skateboard manufacturer. It's the same people, whatever, that were in question number 6. We don't need information from question number 6 to do this problem. We know that our constant yearly demand is 2,100 skateboards. It costs $500 to spin up the factory for production and $25 per skateboard. Additionally, it costs $10 to store each skateboards for a year. How many skateboard orders should you make annually to minimize your costs? In other words, how many orders do you need to make per year, right? So I gave you the total cost equation here, that C of n is equal to Fn plus Vq plus Sq over 2n. And recall that F is the fixed startup cost, so that's the amount that it costs to spin up the factory. So for this problem, F will be $500. And our V is our variable cost per unit. So in this case, V will be the cost per skateboard, which is $25. Q is your yearly quantity demanded, which is 2,100 skateboards. And S is your cost to store each unit for a year, which is $10. So in this situation, we should end up having just n left over, and that's fine because n is our variable. That's the thing that we're actually going to be optimizing. So these lot size problems, they don't really have a traditional constraint in the same way that other optimization problems have. Their constraint is sort of something that is just given in the statement of the problem. So between this and the profit revenue cost type problems, these are sort of the easiest things to optimize once you have the formula. Right. So let's see here. If we have, let's plug in all our numbers and simplify some stuff. So C of n is Fn plus Vq plus Sq over 2n. So C of n is 500 n plus 25 times 2,100 plus 10 times 2,100 divided by 2 times n. We can simplify a couple things here. 500n plus 25 times 2,100 is 52,500. 10 times 2,100 divided by 2 is 21,000 divided by 2, which should just be 10,500. Why don't we go ahead and actually just plug that in so I don't make a stupid mistake. Yeah, 5250. Oh, what am I doing? 10.5 plus 10,500 over n. Okay. And now we need to take the derivative of this function, just like we have for all the other optimization problems. So we need to find C prime of n, which is 500 plus this 52,500 just disappears. It turns out that your variable cost per unit doesn't affect what your lot size is. The thing that really matters is the cost per order and the cost per for storage. So your variable cost will always drop out of this equation. And in this case, we should end up with 500, minus 10,500 divided by n squared. This is the same derivative that we've done about 3 times already today, right? 10,500 over n is actually equal to 10,500 times n to the negative 1, and we can apply the power rule and then simplify it back. I'm just skipping the step since it's the same thing we've done 3 times already today. Okay. Any other questions about the derivative? Now we're setting the derivative equal to 0 and finding our critical points. So 0 is equal to 500 plus, minus 10,500 over n squared, which means that 10,500 over n squared is equal to 500. We can multiply both sides by n squared, so 10,500 is equal to 500 n squared. And then we can divide both sides by 500. Whoops. To give ourselves 21 is equal to n squared. So then n is plus or minus 4 point, let's call it 5.8. So notably for this problem, we can't make 4.58 orders per year. So first off, we can throw away negative 4.58. Why can we throw away negative 4.58?
Can't make negative orders.
Yeah, orders has to be a positive quantity, right? So there's no way to possibly make a negative amount of orders per year. So we get rid of that one. So we're just thinking about positive 4.58. We should verify that this is a minimum. So again, I want to use the second derivative test. The first derivative, C prime, was 500 minus 10,500 over n squared. So C double prime will be 21,000 divided by n cubed. Again, we're taking 10,500 over n squared. We're rewriting that as 10,500 times n to the negative 2, and then applying the power rule. To get 21,000 n to the negative 3, and then we're rewriting that as 21,000 over n cubed. But regardless, when we plug in our positive number here, C double prime of 4.58 should certainly be positive, right? So n equals 4.58 is a minimum. So we can't make 4.58 orders per year. You might be able to if you wanted to figure out exactly how many days you should wait between orders. That might actually be the smarter way to do this. But we can figure out which one of 4 or 5 it should be. So we can figure out what C of 4 is and C of 5. So C of 4 will be, we're going to take our C equation, which was this guy here. I was trying to copy and paste. Let's not worry too much. That'll be 500 times 4 plus 52500 plus 10,500 divided by 4. And when we plug that into a calculator, we end up with our cost for making 4 orders being $57,125. And then if we want to plug in 5, we're just changing all of these 4s to 5s. And that one is $57,100. So it's slightly more efficient. We should make 5 orders per year to minimize costs.
Oh, can you please go up a little? I didn't get everything. That's good.
Okay. All right. So these lot size problems are, they're actually really not that bad once you've done a couple of them. You're just applying the formula and then you're doing the same steps for optimization as anything else. The only trick is at the end you need to find a whole number approximation. That could be true for a handful of these other things too. You may not want to, like for instance, if you walked into a department store or a hardware store and you said, "Hey, I need some 8.66 foot long pieces of wood," like the guy is just going to say, "Okay, so you mean like 8 feet and 8 inches?" Like units in the real world end up being the things that actually you'll use them in a way that actually makes sense rather than a way that is exactly mathematically correct. So the best you can do is find something that's close enough to ideal, but also works within the constraints of the world we live in. So, all right, can I move on now, Connor?
Yeah.
Cool. All right, so let's do maybe one more of these, and then I'm going to let you guys go. And I want you guys to make sure that you're working on your project stuff. Those of you who haven't got in that product statement, I need that as soon as possible. And I will also let you work through these problems a little bit more. And then we'll have another sort of set of problems on Monday for the test. Would we rather look at number 5 or number 6?
No,
I'm guessing Connor was voting for number 5 there.
no, I meant 6.
Okay. Yeah, so number 6 is another price revenue cost type problem. So let's go ahead and let's pull this down somewhere where we have some room to work. Let's pull it up here. So number 6 asks, you work at a company that manufactures and sells skateboards. Your accountant finds that your monthly demand price function is given by P of X is equal to negative 0.1x plus 60. This is little P of X, this is demand. Okay, and your monthly cost function is given by C of x is equal to 25x plus 2,000. Where x is the number of skateboards produced and sold. What price points should you set for your skateboards to maximize the profit? So in this situation, I'm looking for a profit equation, but I didn't give you a profit equation. I gave you a price or a demand equation and a cost equation. So we need to figure out revenue, and then once we have revenue, we need to figure out profit. So first off, remember that revenue, R of x, is equal to price times x times quantity. So our revenue equation is actually negative 0.1x squared plus 60x. Our cost equation will then be used to find our profit equation. So profit is equal to revenue minus cost. So our revenue is negative 0.1x squared plus 60x minus our cost equation, which is 25x plus 2,000. Let's simplify this out a little bit. So our profit equation, P of x, is negative 0.1x squared plus 35x minus 200, or 2,000, sorry. One common mistake that I see, and I think I've mentioned it about a million times, and I'll mention a million times more, when you're subtracting off the cost, you need to subtract off the entire cost. You need to distribute that negative sign to both your variable part and your fixed part of your cost, okay? So make sure that happens. That's why that 2,000 is actually negative. So let's go ahead and find our derivative. The marginal profit, P prime of x, is going to be negative 0.2x plus 35. And then we're going to set that equal to 0. So 0 is equal to negative 0.2x plus 35. We can add 0.2x to both sides. And then multiply both sides by 5. So x will be equal to 175. So since x is equal to 175, we should test this value. This is even more straightforward to use the second derivative test than any other one we've looked at so far. P double prime of x is just negative 0.2. So P double prime of 175 is also negative 0.2. So x equals 175 gives a minimum. Sorry, a maximum. Concave down makes a frown. So we're at a maximal point here. So this tells us that we should be selling 175 skateboards. But it doesn't tell us what our price should be set at, right? It just tells us what our profit should be, or what our the number or quantity should be. So what price should we be selling at in order to fit 175 skateboards, right? In order to do that, we need to go back to our demand function. So the price of a skateboard is little p of x is equal to negative 0.1x times, or sorry, negative 0.1x plus 60. right? That was the equation from the... Yeah, 0.1x plus 60. So now we just need to plug in x is equal to 175. So little p of 175 is negative 0.1 times 175 plus 60, which is negative 17.5 plus 60, which is, I believe, 42.5. So we should charge approximately 42.5 per skateboard. In order to maximize our profit. And these are really common problems. So I would expect to see on the take-home test, I would expect to see a problem where I ask you to go all the way up from like a little bit of basic information. Like, you know, on that first test, I gave you a bunch of like, here's your fixed cost, here's your variable costs, here's a couple of points to make your profit function out of, right? So these things are, and then build all the way up to making a profit function and finding the optimal price point. And that's more or less what your guys' project is asking you to do, except you're gathering a little bit more data to do your approximation of your demand function a little better. Any questions about number 6? All right. So on Monday, I'll give another set of problems on optimization that resemble the types of problems I'm going to ask you for on the exam. And then on Wednesday, I will hand out the exam. On Wednesday, you guys should expect, since the exam is a take-home exam, I think that I'm actually going to cover new material on Wednesday. But that material that is covered on Wednesday you will not be responsible for it on the test. You will be eventually responsible for it, but you won't be responsible for it on that specific test. Okay. Does anybody have any last-minute questions before I let you go?
So the sections for the exam is from the last exam to what we've covered so far.
Which is basically an optimization.
Okay.
So you should expect to see, again, I haven't come down firmly on one of these. You should expect to see between 4 and 6 optimization problems that will be relatively involved types of things. And then that will be the exam. You'll pick some amount of them, probably 5 out of the 6. Do those, write up your answers, and submit them on D2L.
Will there be a Dropbox for that? Or
Yeah, I'll put up an assignment for it. Okay. So I will be sort of on call for the next hour or so until 4:50. I will hang out in one of the other voice channels. So if you would like to ask me any questions about these problems or any other questions you have, I will be definitely on hand for the next hour. Other than that, you guys are free to work on these problems or whatever it is that you want to do with the rest of your time. So.
When we start to take our test next Wednesday, I might have a little trouble because I'm not really used to writing math problems on a computer.
So I would be okay with you taking pictures of your work and submitting the pictures.
Oh, okay. Yeah, that.
Yeah. I would. Yeah, I'm not 100% sure how I want to handle it, but that would probably be a viable option. So. All right. I'm stopping the recording and jumping down to the other channel. See you guys on Monday or later today if you guys need to get a hold of me.